Chapter 6. Some Rules of Probabilities. In statistics, an experiment is one for which the outcomes cannot be predicted with certainty. We can specify all possible outcomes, and we can repeat the experiment under the same conditions or under essentially the same conditions. Tossing a coin or rolling a die can be considered as experiments in statistics. By a sample space, we mean the collection of all possible outcomes of the experiment. For example, when we toss a coin, there are two possible outcomes, head H and tails T. The sample space is the set S that contains the two outcomes that are H and T. Rolling a die is an experiment in which the sample space contains the numbers 1, 2, 3, 4, 5, and 6. Tossing a coin repeatedly until a head turns up is an experiment in which the sample space contains outcomes H, TH, TTH, TTTTH, and so on. Notice that the sample space can be a finite set or an infinite set, as in this case. In this example, we are rolling two dice, one white and the other red. We have many outcomes in this case. One such outcome may be 3 on the white die and 5 on the red die. A table can be given to show all possible outcomes. This figure shows all 36 possible outcomes when we roll the two dice. Ordered pairs can be used to help represent the outcomes. Notice the sample space contains 36 ordered pairs. Each one of them corresponds to a possible outcome. An event is a subset of a sample space. This means that an event is a collection of outcomes. For example, when tossing two different dice, the sample space consists of 36 outcomes represented by ordered pairs. The event that a sum of 7 turns up is a subset of the sample space consisting of the outcomes 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Since events are sets, then operations performed on sets can also be applied to events. If A is an event on a sample space S, then the complement of A, denoted by A prime, is the event that occurs whenever A does not occur. A Venn diagram can be used to represent the event A prime. If A and B are two events on a sample space S, then A intersection B is an event. This event occurs whenever both A and B occur. In the Venn diagram, the event A intersection B represented by the overlap parts of A and B. If A and B are two events on a sample space S, then A union B represents an event. This event occurs whenever A occurs, or B occurs, or both A and B occurs. Again, we can represent this event by a Venn diagram. We say that two events A and B are mutually exclusive or disjoint if their intersection A intersection B is the empty set phi. Properties applied to sets also apply to the events. This is because events themselves are sets. You see here a few properties of events. In this example, 3 sets A, B, and C are indicated. Each set represents certain colors. For example, A represents the colors blue and green. To simplify the process, we can use numbers instead of colors. So A contains the numbers 3 and 4. Some operations on these sets are performed here. The following three postulates represent the basic rules of probability. The first postulate states that the probability of any event is a real number greater than or equal to 0. The second postulate states that the probability of any sample space is 1. The third postulate states that if two events are mutually exclusive, the probability that one or the other will occur equals the sum of their probabilities. Many other rules can be derived from these three postulates. For example, probability of phi is 0. Probability of an event equal to 1 minus probability of the complement of that event. Probability of any event is a number between 0 and 1 inclusive. And if we add the probabilities of all the outcomes of a finite sample space, the result will be 1. When we say that the odds are in favor of an event are A to B, we mean that the fraction A over B is equal to the ratio of the probability that the event will occur to the probability that it will not occur. In symbols, this means A over B equals P over 1 minus P, where P is the probability of the occurrence of the event. We can obtain P in terms of the odds by solving the formula for P to get P equals A divided by A plus B. In example 7, we are told that the odds are 4 to 1. This means that A equals 4 and B equals 1. Therefore, we can find the probability of the event. This probability equals A divided by A plus B, or 4 divided by 4 plus 1, which is equal to 4 over 5. In part A of example 8, we start by finding P, the probability of rolling a number less than 5. Since there are 4 outcomes in this event, namely rolling 1, 2, 3, or 4, then the probability is 4 over 6. Using the formula, we see that the odds are 2 to 1. In part B, the probability of drawing a heart is 13 over 52, or 1 over 4. Again, using the formula, we see that the odds are 1 to 3. Here we introduce the addition rules of probability. The first rule is the same as the third postulate. If we have two mutually exclusive events, then the probability of their union equals to the sum of their probabilities. In 2, this is generalized to any finite number of mutually exclusive events. Rule 3 works for any two events. In this case, the probability of the union of the two events equals to the sum of their probabilities minus the probability of the intersection of the two events. In this example, the probabilities of what to do for lunch are given. Observe that the sum of these probabilities is equal to 1. To answer the given questions, we use letters to represent the different events. Then we express the required probabilities in terms of these letters. Notice that the events C, B, R, H, and S are mutually exclusive. We use the addition rules of probability to answer parts A, B, and C. For part D, we use the rule that states that the probability of the complement of an event equals 1 minus the probability of the event itself. When we have two events on the same sample space, we can talk about the probability of occurrence of one event given that the other event has already occurred. This probability is called the conditional probability. In symbols, if A and B are two events, then the probability of A given B is defined to be equal to the probability of A intersection B, divided by the probability of B. If the conditional probability of A given B is the same as the regular probability of A, then we say that the events A and B are independent. If this is not the case, we say they are dependent. Here we introduce the multiplication rules of probability. The first rule follows from the definition of the conditional probability. It states that the probability of the intersection of any two events equals to the product of the probability of the first event and the conditional probability of the second event given the first event. The second rule is for independent events. In this case, the probability of the intersection of two independent events equals to the product of the probabilities of the events. In this example, we are given the probability of the event H, the probability of the event C, and the probability of the event H intersection C. It turns out that events H and C are independent. We can show this in two ways. The first way is by using the definition of independent events, and the second way is by using the multiplication rule for independent events. Bayes' theorem was developed by Reverend Thomas Bayes, years 1702 to 1761, an English Presbyterian minister and mathematician. Bayes' theorem represents an expanded form for conditional probabilities that allows us to adjust or revise the probabilities assigned to events in accordance with new information. Bayes' rule is given here. Notice that the denominator in Bayes' rule equals to the probability of A, which is obtained by the rule of total probability. A tree diagram can be helpful when applying Bayes' theorem. In this example, we use the rule of total probability to find the probability that last year's winner will repeat.